important points are two. First is that there is a singular term there which is originating from self-correlation of the same level where this n and m are the same. And then important thing is that the density, even the fluctuating one, not the average one, integrated over all energies must give the total number of levels which does not change. It doesn't fluctuate. So this thing is fluctuating, but the integral is not. And then the consequence of that was some rule for the non-trivial part of the correlation function, and then it can be written in different ways, and the most simple way is this, where the delta function which is present in the correlation function is integrated, and then what remains is such a sum rule. And then also I told you that it is useful to make so-called unfolding. This means that instead of the energy, you introduce a different variable, and the density in this variable, the average density, is equal to 1, and then in terms of these variables, this sum rule looks like this. Then I told you that this sum rule is exact when integration is from minus infinity to plus infinity, but the number of levels, size of the matrix, size of the system is finite. And these two operations, sending n to infinity and integration from minus infinity to plus infinity, does not commute, and therefore I gave you an example of the simple random diagonal matrix, and I have shown that this non-trivial function y in this case is simply minus 1 over n, so it is very small but very wide. And so if I do the integral, then I will get indeed minus 1 as the sum rule requires. But if I first send n to infinity, then this function will be 0, and the sum rule will be violated. And therefore, this statement about the violation of the sum rule when I first send size to infinity, this is a general point, and in this sense, Wigner-Dyson matrices are exception, because in this case I can send n to infinity first, and the sum rule is not violated. So this is related with some incompressibility of the Wigner-Dyson plasma. Okay, so now okay. No, this is not. How it come here? I don't know. Okay, so there was some reshuffling of slides. Okay, and this is the picture which I made by hand on the whiteboard, but this time I did it in a real shape. So this blue line is this is the non-trivial correlation function or irreducible correlation function of Wigner-Dyson for the unitary ensemble for simplicity. Therefore, here it is locally a parabola and with a minimum at -1, and then as this distance between the S and S prime goes to infinity, it approaches 0, and it approaches 0 while making some oscillations, and the period of these oscillations in these variables is exactly 1, because this variable, as I said, it is essentially the energy in units of mean-level spacing. So this is an exact for Wigner-Dyson unitary case. For orthogonal case, it is a bit different. So here it is a linear behavior, as we know. But what is important is that we, from the plasma model, we computed this irreducible part of the correlation function. It appears to be E minus E prime and inverse square. And if I plot this, if I make rescaling, make unfolding and plot it on out here, so what I will obtain is this dashed line. So this dashed line is what plasma model gives. And here it is divergent, and this tells you that the plasma model gives you the answer, which is the envelope of this oscillation. So it is, it goes through the middle point of the oscillations, and plasma model is not able to reproduce scales like mean-level spacing, but it is able to reproduce scales which are much bigger, so it gives you an envelope of this function. And here it is absolutely fails because it is divergent 1 over S minus S prime squared, but this is a scale smaller than 1, where we do not expect this plasma model giving the correct answer. But then, since it is not well visible how exactly it approaches 0, what I did, I plotted the same, but I plotted minus y, which is positive, in the log scale. So I took the log scale over y-axis, and this makes you visible what happens when the function is small, and at certain points 1, 2, 3, and so on, this function touches 0, therefore logarithm goes to minus infinity. Here it is the usual scale, so it goes to 0 here, and this maximum are this in the linear plot, and so it is now seen how this plasma model gives you an envelope of the real function, even when it is as small as 10 to minus 3 and even smaller. So this is a proof that this plasma model gives you an answer which is very accurately the envelope of this oscillation function. And okay, so then we come to a new statistics, and this statistics is the following. Suppose you have, it is so-called level number variance. So what you do is this. So
Vladimir, how to understand that there are points where there is how to understand that there are points where there's no correlation in the spacings in Wigner-Dyson. I mean, you have strong level repulsion, right?
Yeah.
So these singular points, they are more like Crawthorne.
You mean why it touches zero at some points?
Yeah.
Look, it is a property of I don't know. I cannot explain it my finger because this is not. This is only for unitary ensemble. If you take orthogonal ensemble, it will not touch zero. So it will be oscillating. It will be having an envelope which is 1 over s minus s prime squared, but it will not touch zero. So it is a peculiar stuff of the unitary ensemble, but the level repulsion actually is this deep is the level repulsion, because this is what? This is the irreducible part of the correlation function. And full correlation function, besides delta function, it is 1 plus y. Where this guy, and this is the full correlation function, R of S prime. And at s equal to s prime, this guy must be -1, and this is the level repulsion.
Okay, yeah.
Because there is a shift by 1.
Yeah.
Okay? And the fact that it touches zero at some points, look, this is, I don't know, so how to explain it? This is not a generic thing. This is only for the unitary ensemble. Okay, now in new statistics, which Simon knows very well, this is the level number variance. So this is the following. You have energy, you have energy levels which are random, and you take a small window, so energy levels are everywhere here too. You take a small window, small compared to the total width of the spectrum, but it may be large compared to mean level spacing, and you fix this window, and then you ask a question: what will be the deviation from the mean number of levels here? So if you fix the energy, you fix the mean number, because the mean number is the width in the energy divided by mean level spacing. So the mean number is fixed, but the real number is fluctuating, and this fluctuation is quantified by such things. This is the deviation from the mean, squared average, and this is given by this formula, and so the question is how much this spectrum, the number of levels, is fluctuating. So this thing is generally depending on an average on the width of the energy window. And how does it depend? This is now a question. So this is a simple exercise, in fact, because the mean number of levels is an integral of the mean density over the energy window. It's clear. Now, then, if I take this integral twice and then average, I will get mean squared. So then, if I want to have n squared average minus n average squared, so I combine these two, and then what I have, this is just simple algebra. So what I'm getting of course this prefactor, which comes essentially from this thing and taken twice because n average square, and also from the definition of R function, which is the level density correlation function divided by the average. So then, if I multiply this R function by this thing, I cancel this normalization, and you have exactly this formula. Now then, so this part gives you n squared average, and n average squared comes from this minus 1. So this is a simple thing, and then I recall you that again the definition that R is 1 plus y plus delta function of s minus s prime. This is just definition, and then this 1 cancels this minus 1, then there will be irreducible part and the delta function, and then
sorry. So do I understand correctly that all this works in case when average n is, or delta E is way bigger than 1, when there is like a lot of states in our window? Otherwise we would not be able to use the integrals.
So I didn't understand. This is a general thing. So I just once again I didn't understand the question.
Okay. So
no. You should not hesitate to ask any question.
Yes. Very stupidly. So far you're just rewriting. That's it. There was no approximation.
This is absolutely general thing.
Okay.
So it is based on the fact that if I take the density which is fluctuating, integrate it over energy, I will get the number of levels also fluctuate.
Yes.
So this is a general thing, and then I want to make some other. Simple thing. Why? Because when S and S prime are much smaller than the total width of the spectrum, then usually for situation of we will be talking about exceptions, but usually when S and S prime are much smaller than the total width of the spectrum, so when the energy is much smaller than the total width of the spectrum, but S then is much smaller than the number of levels, then this guy depends on the difference. So of course there are corrections, but these corrections are of order S or S prime divided by A. So if I neglect these corrections, then this guy depends only on the difference. And then there are two integrals here, but the function depends only on the difference. So what is useful to do is to change integration over ds and ds prime, here ds prime, and switch to integration over ds and over the difference. So it is simple thing. The Jacobian of this transformation is 1, and then So I will not do it here on the plan, but so how to switch from integration over ds and ds prime to such things. This is only to set a correct boundary, and the correct boundary for this difference will be from minus n to plus n average instead of 1/2, because there could be 1/2 here and minus 1/2 here, and then we will be. Then when I do so, I can integrate over ds first, because this function does not depend, with this assumption, this function does not depend on s and depend only on the difference. So I can make this integration without knowing anything about this function. And when I do this, when I integrate over ds, it's a very simple thing. What arises is this factor. I can do it, geometrically. It's simply a geometric factor. So you write the boundaries of your. So you first have your integration. Initial integration is over such minus n over 2 n over 2 over such. This is s prime and this is s. And then what you want to do, you want to instead integrate over s and over the distance s minus s prime. And distance s minus s prime, here this distance is 0, here this distance is something. And you see that this integration over ds, it goes in a finite region from here to here. And this gives you this factor. So then and also there is a delta function which I do not have to forget. And this delta function gives you this delta function plus this factor gives you an average. So what you have, it is again absolutely general formula that the variance is given by an average plus the part that depends on this irreducible correlation function, which takes into account level repulsion. It is negative. So then, first of all, I have shown you an example of the random diagonal matrix, and in this example, you have this y function like this. It is minus 1 over n from n over 2 to minus n over 2. And when I send n to infinity, this function becomes 0. So, what is important? Important is that here the limits of integration are finite. So for this normalization sum rule, they were infinite. And here they are finite. This is the average number of levels in a window. And when they are finite, so okay, I can safely send n to infinity. And when I send n to infinity for this random diagonal matrix that essentially gives you Poisson statistics. This guy goes to zero, this term vanishes, and you indeed have that your variance is equal to n average. And this is a known property of the Poisson statistics, that any moment is equal to n average. So this is just the property of the Poisson statistics. But this formula is absolutely general. Okay, and now I want to apply this formula for the Wigner-Dyson case. And it appears that the plasma model is enough to compute this the main part of the variance, of the level number variance. So first of all, I take this formula, and I take into account that this y of n is an even function. It is less general than this formula, but for confinement potential, which is even, this is an even function. So if I take into account that it is an even function, I can write down 2 and integrate over positive part of it. And then it is very important. I have to take into account that there is normalization sum rule. So you see this part. This normalization sum rule also could be written as 2 integral from 0 to infinity. But the difference is that here the integration is to infinity. And in this formula, which I have shown here, the integration is from 0 to average number of particles in the window. So what I do, I use this thing and I rewrite the formula, this formula, I rewrite in the following way. So this is a simple thing that, the integral from 0 to infinity is the integral from 0 to n average plus integral from n average to infinity. And okay, I can do it on the blackboard, but you can repeat it any time. So it is simple to use that the integral from 0 to infinity is minus 1/2. And what I actually need, I need the integral from 0 to n, and this integral from 0 to n is the remaining part, is the integral from n average to infinity. And why this is a useful transformation? Because from the plasma model, I know this guy only at S, which is much bigger than 1, which is much bigger than the mean level spacing, as I have shown you on this picture. So in this region, it gives you very well at the envelope, and here it fails. So if I want to use this result from the plasma model, to use it to find the integral like this, I have to exclude the region which is close to 0. And in order to exclude this region, I use this sum rule, because here this region close to 0 is is taken into account. And so when I rewrite this formula, general formula in this way, then here the integration goes from n average to infinity, and when n average is much bigger than 1, then I can safely substitute this function and it gives the correct result. So then what I do, I substitute this function to here, and I have two paths. So you see, this path is formally from 0 to n, but we know that we cannot go down to 0. We should cut this integral at s of the order of 1. And usually, if I make such a cut, I make a big mistake. But here, there is a special case where there is a logarithmic integral, the integral ds over modulus of s. And when you have a logarithmic integral, then putting here some cutoff, for instance, if I have the integral ds by s from a to infinity, so what do I have? I have the not to infinity, to n. What do I have? I have a logarithm of n minus logarithm of a. And when n is big, n is much bigger than 1, then this is the main term, and this is of order 1. So this logarithm is big, and this is of order 1. And if you want to have only the leading term, then you can put here any cutoff which is of order 1, and it will be leading to some subleading path.
Sorry. But I mean, as far as we're working in plasma model, right?
Huh?
As far as we're working with in plasma model,
Yes.
we have no idea what is happening at s, which are way smaller. So is it possible that under this cutoff, with real y, which is not for plasma model,
No,
but
of
for
course.
random matrix, there would be something big?
No, of course. Later on, I will obtain the real one.
Okay.
And the real one I can put here in the same formula and get the same result, the same leading path. So
okay.
there will be, if I put the exact formula, so what I will get not only correct logarithmic term, but also correct term like this.
Yes, exactly.
But what I want to tell you is the following, that in physics, in theoretical physics, it is always necessary to make some approximations in order to get some answer. And because, exact solutions are a rare thing, and you have to make many calculations. And what I want to tell you is the following, that if you see a logarithmic integral, this is a gift from the Lord for you. Because the logarithmic integral can be cut at any value here, and it will be a subleading term. And this is not the case for, let's say, for integral which is a power law, which is power, because for the power law, it is, if it is divergent, let's say power 1 plus alpha, then this guy will give a very significant contribution. So the logarithmic situation is a gift, and this is for any problem. For instance, there is such things like renormalization group in physics, and all this renormalization group, the whole idea of this renormalization group is based on the so-called logarithmic situation, because you have a product of logarithms, and you can treat them not in an approximate way. The simplest example is this. And therefore, I'm asking this. I'm showing this to you because you know it is an approximate formula. Nevertheless, it gives the leading term correctly. So again, if I put this into here, I have two things. So this is a logarithmic, an integral which gives you the logarithm, and then some some term of order of 1, which depends on exact form of this y. So if I'm not interested in this correction, and I'm interested only in the leading term, then I put any cutoff here, extract this leading term, and it will be like this, following this formula. Of course, there will be correction of order 1. So this is a big number if n is large, and this is a correction. Now there is the second term. And the second term, if I integrate it, it gives me 1 over n average squared. Sorry. Yeah, even not squared. 1 over n average. So ds by s squared gives you 1 over s, and you substitute n average, there will be 1 over n average. And here there is an average, so they cancel out, and I have again a term of order 1. So some term of order 1 appears from here, it's in addition to logarithm, and some term of order 1 appears from here. And if I'm interested only in the leading term, I'm done. If I'm interested in what is exactly this term, I have to use an exact function. Okay, so this is all, and now I come to the definition of what is called level compressibility. So first we have this exact formula valid for any situation, and level compressibility by definition is the derivative of this guy with respect to n average. So when I do this derivative, so the first term is 1. Then when I do derivative here, so I can differentiate with respect to upper limit or lower limit. But this differentiation means that I have to substitute instead of s, upper limit or lower limit. And this factor will be 0 in most cases. And then there is a differentiation with respect to n inside the integral. And when I do it, so I will get this result. So the level compressibility very generally is like this. But then everything depends on now on the shape of this formula, and let us compute this level compressibility for two limiting cases, for the Wigner-Dyson case and for the Poisson case. For the Poisson case, when n goes to infinity, then this vanishes and the level compressibility is just 1. For the Wigner-Dyson case, okay, again, I can, instead of computing this integral, so of course if I have this function exactly, I can compute it exactly and see what happens. But if I don't have it exactly, but I have only the approximate value from the plasma model, what I can do, I can use this formula, which eventually leads to this, and then when I differentiate it with respect to n average number of levels, so this will go away after differentiation, and this will give 1 over n average. And then the Wigner-Dyson level compressibility is 1 over n, and when n is big, it goes to 0. So for the Poisson case, it goes to a finite limit, and for the Wigner-Dyson case, it goes to 0. So one can say that the limiting level compressibility when n goes to infinity, but after, so basically n goes to infinity, but n by n goes to 0. This is the right limit. So this means that the number of levels goes to infinity first, and then n goes to infinity after that. And then you have the level compressibility 0 for Wigner-Dyson, and you have it 1 for Poisson. But it is interesting that there are critical cases which realize in, let's say, in the critical point of the Anderson model. They realize in these power low-banded matrices with a certain choice of parameter. We will discuss it later. And also is realized in allometric model, which I briefly mentioned. And in this case, it appears that it is possible that the limiting level compressibility is not 1, is not 0, but something in between. And this is an important characteristic of the critical state. So, okay. And now let us consider a very interesting example. It is very interesting, very peculiar. And this is an example of shallow confinement in which confinement potential is like this. So I have already discussed this situation, and I have found that the mean density behaves like 1 over energy. And it appears to be very important that it behaves exactly like 1 over energy. Why? In order to understand why, we should first do this unfolding. So unfolding means that instead of, we should define a new variable s such that this relation holds. Then this s is the integral from 0 to e of the mean density. And this integral is logarithmic. And also it has a sign factor, because if e is greater than 1, it is positive. If e is smaller than 1, it is negative. So this is the unfolding a new variable in terms of the old one for this particular case. But then, of course, I can inverse, I can reverse this relation and find e as a function of s. And this e as a function of s will be exponential. So this is logarithmic, this will be exponential. And this is This is extremely important that it is exponential. So now I want to do the following. I want to make unfolding for this we consider plasma model. We found for the plasma model that this irreducible part is E minus E prime squared. But this is for the irreducible part of the correlation function. But when I want to discuss this R function, I have to normalize it by the product of the averages, and that's why if I want to deal with this y function, so it is the irreducible part of the density correlation function divided by the average. And now let's see what happens. So this is for just substitute E in terms of x. And this is remarkable. It's so remarkable that I repeat this simple calculation here. So, okay. So, what is E? E is exponential of s by gamma and then sin s. What is E prime? E prime is the same exponential s prime by gamma sin s prime. And this is squared. And then it is divided by rho, and each of this rho is 1 over E. So then in the numerator there will be E to S by gamma sine, then E S prime by gamma, also sine S prime, and then let us see what it is. So I can put this two exponentials here like e to minus s prime over 2 gamma, and here I can put it like so I just cancel it here and put it there, and then e to and two of them, of course, e to s prime by gamma, and here as well minus s by gamma e s prime by gamma over 2. And now, then I can write here unity, and now I can look what is it. So first of all, let's consider the situation where s is positive and s prime is also positive. So then what I have here e s over 2 gamma. These two give me this result, and then I have plus s prime by here should be 2 gamma by 2 gamma, What I have, I have this yeah, I have this thing, so it is an exponential of the sum essentially, and here I have minus e exponential of here there will be s prime by 2 gamma, these two things, and here there will be yeah, it will be s prime by 2 gamma. Sorry, something went wrong. Just a moment. Something went wrong. So minus e prime. Okay. So and then there is this guy. Sorry, I think I made somewhere a mistake, because what should happen, what is the correct result is that here there is a difference s minus s prime, and here there is the difference s prime minus s, and what I see here is not really this thing. So just a moment. So s is positive, s prime is positive, right? Okay. Sign does not matter. Not is modulus of e. Not is modulus of e. Sorry. Sorry. No, it is. I'm sorry. So there should be 2 minuses here, because rho naught is 1 over e. E is an exponential. So when rho naught goes to when in the numerator there should be e by e prime. So they will be both with the sign plus. When they go down, they will be both with the sign minus. Okay, and now it is correct. Now this will be s by 2 gamma, and this will be minus s by 2 gamma. And this guy will be s prime by 2 gamma from here, and minus s by 2 gamma. Okay, and this all squared to minus second power. And this will be sine hyperbolic of this thing. So when s and s both positive are both negative, you can check when they are both negative is the same thing, then there will be sine minus 2. But when one of them is positive and the other is negative, then these signs here will result in the following, that the signs will be different here and here, and so here there will be plus. And then also you should take into account the models, which is let's say s is positive, s prime is negative, then then here there will be not minus but plus, and here if S is positive, then this is this is like this, and when this guy is negative, it will be also with the sign minus. And what I will get, and here there will be sign plus because of different signs of these sign functions. And so I will get hyperbolic cosine. So you see what happens. So if I log this function, so and this is already the
Sorry, may I ask a question? The formula in red box, the formula for gamma infinity was
This one?
It appears from like previous calculations, or
no, it appears from, as I said, it appears from plasma. It appears from plasma. This is this formula.
okay.
The only thing is that this is a rho correlation function.
Yes.
But y is related to r correlation function, which is
Okay.
which is normalized by.
Yes. Okay.
It is normalized by
Thank
2.
you.
So it is following from general things. So you see, such an interesting thing, and this calculation is only valid if you have exponential functions. And then I plot you how does it look like. So if you take this formula literally, so what you have some, you have a negative correlation function because it is so-called level repulsion. But now it is quite weird level repulsion because there is one correlation hole at S equal minus S prime, and the other correlation hole at S equal plus S prime. So when I consider literally what comes from the plasma model, this part will be divergent because when S goes to S prime, this goes to infinity. But in fact, if you take an exact calculation, this should be multiplied by the sine function, and then this divergence is cut, and what you get a finite deep, and then why it is amazing, because we did an unfolding, and now mean density is unity. In these S variables, mean density is unity, it is constant. Nevertheless, the translation invariance, so you would expect that this function depends on the difference. But in fact, it doesn't depend on the difference. It depends on each variable separately. Because if they would depend only on the difference, there will be only one deep. And you have two. So this is the example how shallow confinement, weak confinement, how it corrupts the results for big Dyson. First of all, first what it does, it violates the translation invariance after unfolding. So then, what is also interesting, it is the following, that if you take exact function and compute the integral of this 1 plus integral of the negative function, you will get 0, exactly 0. So, you know, in the same way as, and this is the level compressibility. So if I integrate it over this deep and over that deep, I get level compressibility 0. But if I integrate only over this deep, I will get something which is between 0 and 1. And now, what is also amazing is that there is a correlation hole, then exponentially no correlation. So some desert, long desert, and then again a correlation. And this is a really amazing thing. It has an exact solution. I have obtained it from the plasma model, but in fact it has an exact solution. And what is also important, will be discussed later, but I have to mention it now, that if I disregard about this and consider only this part, then this correlation hole will be exactly of the same form as for the critical, let's say, power law-bended matrix ensemble. So somehow there is a very peculiar situation which I personally feel that there is some mathematical beauty here, and I told the mathematicians, but they still moving. The thing is that this model, it is a model which is invariant under basis rotation. The only peculiar thing that makes it different from Wigner-Dyson is a shallow confinement, which is log squared instead of E squared. Now,
sorry. So this shallow confinement, it appears in critical PLP error?
no, shallow confinement,
Yes.
confinement is here.
Yes,
So
yes,
I
I
started
understand.
from
Ah, you just started from
I started
Okay,
from,
okay.
and then I
Yes,
used
yes,
the
yes.
result of the plasma model for O.
Okay.
And then I use the result of the plasma
Yes,
model
yes.
for the correlation.
Mhm.
And then I make an unfolding.
Yes.
And when I make an unfolding, I'm getting a weird thing.
Mhm.
I have two
Yes,
correlation
yes,
holes
yes.
and not one. And but what I want to say, it is even more interesting because this part of this basis rotation invariant case is identical to the correlation function in the basis non-invariant case, like the critical power law bended matrices, like this alchromatic matrices. And this is very interesting situation because I personally think that what happens is the following, that this basis invariant is absolutely unstable. So if you make small perturbation of the random matrix model, such that the basis rotation invariance is broken in some infinitesimal way, then you have completely different statistics of wave function, because when you take it as it is, then the statistics of wave function is trivial, like in the Wigner-Dyson case, because they are decoupled. But the fact that here you have the form of the correlation the same as for critical ensembles, where the basis invariance is broken and where we know that statistics of wave function is non-trivial. It is not like in the Wigner-Dyson case. So I suspect that that this situation with shallow confinement is intrinsically unstable, and if you take if you put some small perturbation that breaks invariance, it will be broken for finite. It will be broken at a finite amount. It is like in magnetics. So suppose you have a magnetic Hamiltonian, and spins up and spins down have the same energy. So you have invariance under inversion of the spin. But then, if you have spins interacting, you put a little bit of magnetic field. So you make spins up and spins down energy a bit different. And what you observe, you immediately will have all spins up, let's say. Or if you reverse magnetic field, all spins down. So this is a spontaneous breakdown of spin direction symmetry. And here I presume that there is a spontaneous breakdown of basis invariance, and for this reason you have apparently basis invariant random matrix model with completely non-Wigner-Dyson correlation function.
Vladimir, when you say that you expect that power law random bandit models are very unstable to slight rotation.
No, not power law. This one is unstable. So power law is stable.
Power law is stable against you.
Power law is stable, but not rotationally invariant from the very beginning.
Yeah.
This one is rotationally invariant from the very beginning. But what I am saying that this rotational invariance can be broken spontaneously. And then the statistics of wave functions will be the same as for the power law. Power law is stable.
Is that something you assume, or you can demonstrate that?
No, it is something that it has never been shown. It is actually some numerical work, a smart numerical work should be done, because you should do the same thing as for magnetic. So, as I said, once again, what is spontaneous breakdown of the symmetry? So you have a magnetic system, and the configuration like this without magnetic field, and configuration like that takes the same energy, okay? But then you apply a small magnetic field which strength goes to 0. And then you may have two different situations. If your temperature is high, then essentially applying such magnetic field will not change anything if magnetic field is very small. But if you are below the, let's say, ferromagnetic transition, then what happens, applying a very small magnetic field, you immediately make a finite difference in the energy, because all these spins are in the ferromagnetic case, they are all like this. And when you apply small magnetic field, but system size goes to infinity, then these two things will produce big change in the energy. So what matters is whether you are in the paramagnetic case. So if you are in a paramagnetic case, it is like this. So you apply this small energy, small field and if there is temperature which is finite, then nothing will change. But here, if temperature is smaller than the ferromagnetic transition, you know that in fact spins are like this, or maybe like this. But if you apply even infinitesimal magnetic field, but such that delta H times n is finite, then the energy of this configuration will be by finite amount smaller than the energy of this. And you will see spontaneous breakdown of the symmetry. So you apply infinitesimal field, but you break the symmetry between such configuration and such configuration by finite amount. And this is one of the ways to see that you have an ordered phase. And what I'm saying is that perhaps here there is a hidden ordered phase, hidden fractal case. And if you do not break the rotation, the basis rotation symmetry, so you say that your wave functions are distributed like for the strong confinement. But in fact, they are not distributed like that. They are distributed. There is some hidden order inside, and in order to reveal this order, you have to break basis rotation symmetry, and then one of these state, which is fractal state, which will be getting the preference. This is my imagination. This has never been shown in a convincing way. Although there were some papers, but it was not shown in the convincing way. But what I am saying is that this is an example how shallow confinement makes the correlation function completely, qualitatively different from Wigner-Dyson. And it is different because it doesn't depend only on the difference. It is different because even if I consider this part, which is approximately depending only on the difference, it will be the part identical to completely different system, to a critical power low bandwidth matrices, and not to Wigner-Dyson. This is the story. And now, since nobody is challenging us, I will give you the last. It seems that nobody there.
I mean, I guess if.
Okay, so this is the last thing. I want to show that this situation, which, it is simply the calculation from, let's say, from plasma model, and plasma model is equivalent to Wigner-Dyson and nothing else. But in fact, it appears that such type of correlation was considered by people who wanted to model the black hole just on the experimental disk. So what was the idea? The idea is the following. Suppose that you have, so what is black hole? I mean, very, very naively. Black hole is when no photons may come out. So everything is inside and nothing may come out, except for Hawking radiation. And so people say, well, it is possible to do the one-dimensional analog of the black hole. So it is, the black hole should be four-dimensional, but this is a one-dimensional analog of the black hole. The idea is very simple. Suppose that you have a tube, and then you make a superfluid flow along this tube. Suppose that you have some constriction here, and then the superfluid velocity here is smaller and here is larger. So for that you have to make something like this. Okay. Now inside this tube there are phonons, because in superfluid the phonons can be generated from the boundary. And then the question is, phonons are analogous to photons. And then the question is, if I am an observer from this end, will I see those phonons or not? And if the flow here is smaller than the phonon velocity, then phonons may exit. An observer will see. Like if you are outside the black hole, because if you are outside black hole, you can see photons. But if here the fluid velocity is larger than the phonon cannot come here. So they are just taken away by the stream, and they cannot come here. And it appears that even mathematics of that is identical to the mathematics of black hole. Mathematics is the following: that there is the space-time, there is some expression for the interval of this space-time and so on. So I'm not going to teach you black holes because I'm not a specialist in it myself. But the fact that this might be like black hole, I explain in very simple terms, because here the phonons can reach the observer and those phonons cannot. Now, there is a paper like this where all this analogy with black holes is given in detail, and the idea was the following: that let us, to realize such things in the, let's say, cold atom system or is perfectly possible. But then, since there is a full analogy with mathematics of real black holes, there should be a Hawking radiation that comes from the horizon of this black hole. So the region where this part there is a switching from this to that. And in this way, one can, on the experimental desk, to see the Hawking radiation, which nobody has seen in the universe, because it is very weak. And there are some estimations what this Hawking radiation should be. But the main idea of this paper is the following: that if you are in a lab, you are like a god. So you can see, you are not like this observer who can see only from this side. You can see overall picture from here and from here. And in particular, you can measure density correlation function of the phonons. So there are phonons there, and there is some density correlation function between these formats. And it appears that this density correlation function should have exactly this form. So there is some entanglement between these phonons inside and outside, and if it is really the situation with a black hole, then you can see these two peaks in the correlation function of density of phonons, and this S will be simply the coordinate along this cube, and instead of level density, you will see density of phonons. And it appears that even mathematically it is the same thing. So it was shown by our paper, which is written quite long ago, and then you see, then even intuitively it becomes clear that indeed these two peaks are separated by the desert, and somehow the correlation does exist between this and that. But if you live in this path, you do not know that this path is present. It seems for you that there is a correlation hole, like usually in the non-invariant ensemble, and then there is nothing. But in fact, because here the correlations are exponentially small. But in fact, there is sort of interior of the black hole where there is this second peak. So it's interesting. It is interesting that this situation with shallow confinement is not only so much different from Wigner Dyson, but there is some reason, some mathematical reason for that. And this mathematical reason can be presented in different way. So I presented it in a simple way, how to construct, how to make an unfolding and to get to peaks. But one can just make this reason more or less the same as the black hole physics, and and then basically these two parts are separated, and here they are indeed separated by exponentially small correlations. But okay, so this is why I'm talking about that. I'm talking again because I want to tell you that different parts of physics are deeply related with each other. They are deeply related if they are indeed deep examples, deep theory. If the theory is not deep, then you will not find any analog. And the fact that this random matrix theory, even in the framework of invariant ensemble or manifest invariant ensemble, you can see a variety of wonderful and I would say quite unexpected things. This is and then the last comment is the following: that this you see the form, the shape of this peak and this peak, it is controlled by gamma, by this parameter gamma. So this gamma is, or 2 gamma, is essentially the width of the peak. And on the other hand, if this analogy is seriously considered, then in this model one can get the Hawking radiation, and the Hawking radiation will be an equilibrium radiation with the temperature like this. So basically, the width of this peak is an inverse proportional to inverse Hawking temperature in this analogy with the black hole. So this again, we study this model of power low bandit matrices, then I will show you in next lectures that it is equivalent to fermions at a finite temperature if these power law bandit matrices are with a critical parameter. And so you see this fact, and again, this temperature which is there, it gives it the width of the peak. So essentially, the fact that critical power low bandit matrices can be associated with a certain temperature, it is a counterpart of this, where this peak can be associated with the Hawking temperature. So there is something very deep here, which is not elaborated down to the end. But okay, so experimentalists did this experiment, and